In this video, we are going to proceed with the second type of improper integral, which is infinite discontinuity. So I just recall what you have learned in type 1. So for type 1 of improper integral, it concerns the area of the region that extends infinitely on the horizontal directions, meaning that the infinite happens on the horizontal direction, let's say on the x-axis, so from negative infinity to a certain interval, let's say a, or from a to infinity, or it can be the interval from negative infinity to infinity. So that is for type 1 case of improper integral. But for type 2, let's say we have a function of fx dx from a to b. So for type 2, it involves the function, this function, that have a limit from a to b, and also it have vertical asymptotes where the integrand or the function has infinite discontinuity at specific point, let's say C here. So at this point, it has infinite discontinuity, or it can be at the end of the interval of the limit. So let's say we have infinite discontinuity at limit equals to b, or it can be infinite discontinuity at point A. So that is type 2, where type 2, it has infinite discontinuity at a certain point in the interval. Now let's say we let S as an bounded region under the graph of fx, and it is above the x-axis between interval A and B. So here at interval x equals to b, the function has infinite discontinuity at x equals to b. So we can find the area of the curve under the curve of fx, where we can write it as integration of fx dx, where the intervals start from a up to t, since at b it is infinite discontinuity here, so we just take it to the closest b, where we define it as t. So the area of AT will approach a definite number of A as t approaching b from the left hand side. So we can say that the integration of fx dx from the limit a to b can be written as limit of a to t, where of fx dx, where t is approaching b from the left hand side, from the left side. This sign of minus refers to the direction from which you approach the interval. For here is RB. So let's say we have limit of fx where t is approaching a point of s naught plus, meaning that the limit as t approaches x naught from the right side, and if the sign here is t approaching x naught from negative, so it means that the limit as t approaches x naught from the left side. So given here, let's say it is x naught, so the limit will be approaching from the right side, and here for negative, it approach x naught from the left side. Now we go through the definition of improper integral of type 2. Okay, for the first part A, we have a case of fx is continuous in the interval a to b, but the function has infinite discontinuity at x equals to b. So you can refer to this graph for A. Then here we can write the improper integral as fx dx from a to b, where we can represent this improper integral as the limit of a to b, since b is the one that has infinite discontinuity. So we replace it as t, where t is approaching b from the left. So it will be, the sign will be negative of fx dx. Okay, the second type is when the function of fx is continuous in the interval a to b, but it has infinite discontinuity at x equals to a. So here our improper integral will be start from the limit of a, where a has the infinite discontinuity, so we represent it as t to b, where t is approaching a from right, so we have plus sign here of fx dx. Okay. So this is the case for B. For case A and case B, if the improper integral is convergent, it means that it has the limit exists, meaning that it has a finite number. The limit has a finite number, and it will be diverged if the limit does not exist. For the third case, which is C, we have a function of fx which is continuous in the interval a to b, except for at point x equals to c. So here we can represent our improper integral, where this will be equals to a to c of fx dx plus from c to b fx dx. So this case is also the same just like the previous type 1, where the left hand side of the integral is said to be converged if both improper integral on the right hand side are converged. But the left hand side of the integral will be diverged if one or both of the integrals on the right hand side is diverged. So it can be diverged and converged, can be converged and diverged, and also diverged. Both are diverged.